Alright, welcome back to Math 1910. We are in Chapter 1 in Section 2, Finding Limits Graphically and Numerically. So this is going to be our first time understanding what a limit is and how we're going to, estimate what that limit is using a graphical approach. And then we're going to learn when limits, here the author uses the words, limits can fail to exist. Okay, but it's when limits don't exist. It's like kind of how I want to view that with you. There's going to be certain cases where limit does not exist. Okay, we're going to get through each one of those cases, and then we're going to basically go through the formal definition of a limit and how to approach and solve for a limit using the formal definition, to solve for the limit. All right, so introducing you guys to limits. We brushed on a little bit last chapter, or my last section, sorry about that, what a limit really is, okay? So we are going to approach this one, graphically and numerically. So if we were to take a look at this graph, okay, you have f of x equals x cubed minus 1 divided by x minus 1. The first thing you tell me is what? X cannot be 1. Why is that? Because that creates division in the denominator by 0. Anytime we're going to divide by 0, all right, the value will not exist there. So that we know that the value at x equals 1 is not going to exist because it creates division by 0. What we need to know is understand what that graph is going to look like. That graph could potentially either have an asymptote at x equals 1, or it could also just have a hole in the graph at x equals 1. You need to understand what this graph is going to look like. We don't exactly know, and also if we plug in 1, we can't get a value of f of x, which is our limit. Okay, because the basic approach to evaluating limits is we substitute in the x value and we get back the y value, and that tells us what the limit is at that particular x value. Well, we can't do that in this case because substituting in the x value creates 0 in the denominator. So we got to understand, all right, I've got either a hole or an asymptote occurring here at x equals 1. Taking a visual approach at this, I know that I can factor that numerator because that's the difference of two cubes. So I know that x minus 1 can get factored out. So I know that this graph is not going to produce an asymptote. It's going to produce a hole at x equals 1. The y value will have a hole there. But let's take a look and see why. So for us, okay, numerically, I want you to put in values into your x and get arbitrarily close to 1. We can't substitute in 1 into your equation, but you can substitute in 0.999, right? You can substitute in 0.99, 0.9. So what you're going to do is you're going to create a table like this. And you're going to substitute in values arbitrarily really close to 1 on both sides of 1. Notice that 0.999, 0.99, and 0.9 are all less than 1. And then we look at values that are greater than 1. So 1.001, 1.01, 1.1. We want to it's not going to help us if we choose, all right, let's look at what happens at 0, let's look at what happens at 2. That is not close enough to x equals 1 to give us a good idea of what the limit's going to be. You have to get very, very close to 1, but it can't be 1, right, to see what it's approaching. So look, you're going to substitute in those values for x. So if we substitute in the value of 0.999 in for x, our y value, our f of x, because it's in function notation, is 2.997. If we substituted in 0.99 for x, we got 2.970. So it looks like from the left-hand side, as I get closer and closer to 1, it looks like the value is going to be 3. Then on the right-hand side, if I substitute in 1.001 in for x. And when I keep saying substitute in for x, I'm talking about into that original equation. The original equation is x cubed minus 1 over x minus 1. I'm going to take that value of 1.001 and put it in for x. So 0.001 cubed minus 1 divided by 1.001 minus 1. Okay, you're going to substitute in. When you do that, all right, you get 3.003. And if we substitute in 1.01 in for x, we get 3.030. So on and so forth. So on the right-hand side of the value of 1, as we plug in values that get closer and closer to 1, our output appears to be going to 3. So what we say is as x approaches 1 from the left-hand side, so that's our 0.9 or 0.99 and our 0.999, and as x approaches 1 from the right-hand side, that's 1.1, 1.01, 1.001, as we approach from the left-hand side and from the right-hand side, it appears that the limit is 3. So our output is 3. The value of f of x will be 3 at 1. Okay? The value doesn't exist, but the limit does. And we're going to get into that in a little bit. So as x approaches 1 from the left and as x approaches 1 from the right, okay, the output appears to be going to 3. And why did we choose 1? Why does it have to? Well, if we step back and look at this, 1 is the point in question, right? If I substitute in 1 there, we get division by 0. So we're always going to evaluate what's going on at the position in question, the position that causes controversy. Okay, so when we take a look at this, all right, we are going to say the limit as x approaches 1 will be 3. Or the limit of f of x as x approaches 1 is 3 is the correct verbiage for that. So on your homework problems, the first chunks of them, you're going to make a table like this. And you're going to use your calculator and you're going to substitute in values that are arbitrarily close to the value in question. It will not always be 1. Sometimes it'll be 0. Sometimes it'll be 2. It just depends on the problem. Okay? If we were to graph this, you can graph this in your calculator. If you graph in the numerator, put it on parentheses x cubed minus 1 divided by parentheses x minus 1, you'll get this graph. And if you look at this graph on your calculator, it doesn't always show the hole. There is a hole in the graph. The hole in the graph is when x equals 1. But we just calculated what's the limit though. The limit is 3. Because we estimated or we evaluated values as on the left-hand side of 1 and the right-hand side of 1. So as x approaches 1 from the left and from the right, the limit appears to be 3. You can see this graphically now, right? There's a hole in the graph there. That's what this open circle represents. Okay, that's a hole in the graph. So what we really need to make sure that we're doing is understanding what the graph looks like, substituting in values. Because if you graph this on your calculator, you will not see this hole most likely. But if you evaluate this on your calculator, you will get no value there. So when you're on your graph and you evaluate x equals 1 there, you're going to get back that it doesn't exist or there's no value there. Okay? But you won't necessarily see that when you graph it on your calculator and just hit zoom 6. So we need to understand that there's going to be holes in the graph and you're going to have to evaluate them there. Because when you plug in the value of 1, you will not get 3 back. You're going to get an error back or does not exist in your calculator. So that's why we have to take and use a table approach. And as it approaches 1 from the left and approaches 1 from the right, what does the y appear to be going to? It appears to be having a limit of 3. So we write our final answer as the limit of f of x as x approaches 1 is equal to 3. 3 is the limit. So we will write our answers in limit notation, which is shown below on the figure here. Okay? So this is what we call the informal definition of a limit. Okay, so the limit of f of x as x approaches c equals L. F of x is our function. So in our first example, that was our x cubed minus 1 over x minus 1. The c was a constant, right? As it's approaching a value in question. So in our last example, c was equal to 1. The limit is what we're solving for using the table approach or the graphical approach, and that our L was 3 in the last example. Okay, so this is the informal definition of a limit and how we write it. And we do that by substituting in the value of c. If it produces where we can't see it, then we got to use the table method, all right, for right now to see what happens as we approach that point C from the left-hand side and we approach it from the right-hand side. All right, let's do another example here. Okay, we're going to estimate it numerically. That means we're going to be making a table here. So we want to evaluate the function here. F of x is equal to x divided by the quantity, so you make sure you have parentheses, of the square root of x plus 1 minus 1. We're going to evaluate that at several points near 0, and we're going to use that result to estimate the limit. Okay, so we write this as the limit of x divided by the square root of x plus 1 minus 1 as x approaches 0. That's how we should formally say that, all right? The limit of f of x as x approaches 0. That's what we're really doing here. So in our case, we got to substitute in values to the left of 0 and to the right of 0. Because right now, if we substitute 0 in, okay, what do we get? We get 0 plus 1 square rooted. So that's the square root of 1. Right? Square root of 1 is 1. And then we get 1 minus 1 in the denominator, which is 0. So we have division by 0. You have 0 over 0. When we have division by 0, okay, we're going to have to take the table approach right now. Later on, there's going to be some other methods we can use that'll make this easier. So for you and your calculator, substitute in values to the left of 0 and substitute in values to the right of 0. So that's what happens here. Okay, you can see the values of x that we're substituting into the left of 0. Make sure you're keeping track of the negatives. Okay, they do need to be negative. And we're looking at values really, really close to 0, but not 0 on the right and the left-hand side. So make sure that you're doing that. When you substitute those values in for x, we get 1.9995 and we get 2.00005. We can see now in our table that as we get close to 0 from the left, right, meaning numbers less than 0, as we get closer to 0 from the right, meaning numbers greater than 0, really close to 0, it looks like we are approaching what value? Well, 1.9995 is really close to 2, so is 2.0005. So we can conclude the limit of f of x as x approaches 0 is equal to 2 in this scenario. So there's how we're evaluating this numerically. We're taking values arbitrarily close to the point in question that we want to take the limit of. We're substituting into the table and seeing where the output, the y values, are going. Okay, so you're going to have to substitute these into your calculator to see how close you can get. And like I said, you need to pick numbers close to 0 in this case, or close to the point in question. Don't pick -1 and +1, because that's not going to give you accurate, and they won't look like the limit is going to the same approach. So if we were to graph this, and once again, this is tough to see on your graphing calculator because your calculator doesn't necessarily graph the whole nice and clean and clear so you can see it. If you put this in your calculator and graph it and hit zoom 6, it would look like it goes through x equals 0. But when you evaluate x equals 0, you would get undefined. So this is why you have to use the table approach. So when we do this, okay, and another reason, you got to pick numbers close to 0 in this case, because if you picked -1, you would get a value of 1, and if you picked 1, you would get a value greater than 2, right? So it looks like the limit wouldn't be going to the same thing, so it wouldn't make sense. So that's why you have to pick numbers that are arbitrarily really, really close to x equals 0, because that's where we, where our point in question is, because that's what causes division by 0 when we do this. Okay? So hopefully that helps in seeing the graph. I think you guys aren't going to have any issue really, substituting into the tables. But being able to approach this, all right, graphically and know that there's a hole there, that's tough to see, okay, with your calculators. So there are limits that fail to exist, or the limit does not exist. We're going to use the term DNE, does not exist, as we move through the chapter here, but limits that fail to exist, because the limits may or may not exist. In the two examples we've done, the limit does exist. The value there does not exist, but the limit does. Okay, as we approach from the left and we approach from the right, The limit was the same, therefore the limit existed. Okay, so we're going to get into the scenarios of when the limit does not exist. Okay, and one of those scenarios is where the left-hand behavior of the graph and the right-hand behavior do not go to the same value. Okay, this happens a lot with absolute value problems. So we want to show that the limit of the absolute value of x divided by x as x approaches 0 does not exist. So first place, right, we have division by 0. So we know that we're going to have some issues anyways when x is 0. So direct substitution here doesn't give us a limit. So now we got to start approaching this. Well, we need to know what this graph looks like. You need to put this graph in your calculator. This is one that's a little easier to approach graphically than numerically if you don't understand absolute values. Remember, absolute values, if we plug in a negative value, we will always get back a positive value. If we plug in a positive value, we will always get back a positive value. So you got to be careful here. What's hurting us is that division by x. So that'll still carry a negative value through for us. Okay, so the best bet is to graph this function. If you don't remember how to graph absolute value in your calculator, when you hit y equals, you hit the math button and you go to number, and then you choose ABS in parentheses, and that will be where the absolute value is, and you put just x in there. All right, close parentheses, and then divide by x when you put that in your calculator. So you should get a graph similar to this. Now remember, your calculator is not going to graph the open circles at 1 and -1 here. Okay, your calculator is not going to do that nicely for you. You have to know that the values there don't exist at 1 or -1. Okay, now what really happens here, or I mean they do exist, but you got to see where they jump. Okay, there's a point of discontinuity here. Okay, but this is the graph of the absolute value of x divided by x. What we can see, the limit does not exist because the left hand side and the right hand side do not agree. So what does that mean? Well, if we were doing our table approach like we did in the first two examples, right, and we plug in values that get closer and closer to 0, it looks like the graph is going to -1. If we take the right hand approach and we plug in values getting closer and closer to 0 from the right hand side, it looks like it's going to +1. Since the left hand side does not equal the right hand side, the limit does not exist. So a rule of thumb is the left hand limit and the right hand limit, well, we're going to get into separate limits later on, but the left hand side and the right hand side, as x approaches c, if they're not the same value, the limit does not exist. Okay, so in this case, the limit does not exist. Hopefully that makes sense. Email me or ask me to Zoom if that doesn't make sense. But we should be able to, visually look at this graph and note, all right, they're not going to the same value. One of them is going to -1, the other one is going to +1. Since the left hand and the right hand side do not agree, they're not going to the same value, the limit does not exist. Okay, so no matter how close x gets to 0, they will not have the same limit, so the limit does not exist. Okay, so what we're going to say is we're going to start defining things in terms of delta, okay, delta x and epsilon. We're going to get into the formal definition of a limit here in a few minutes. Okay, so if delta is a positive number, okay, then for the values of x satisfying the inequality, we can classify them as this following. So negative values of delta, and this is still specific to example 3. So any value of delta, some arbitrarily change in x that we do, as we got closer and closer to x equals 0, we yielded a -1. On the other side of the graph, or on the other side of x equals 0, as delta changed slightly, getting closer and closer to 0 on the positive side, okay, the ratio of the absolute value of x over x got closer and closer to 1. So we notice that the left-hand side and the right-hand side do not change. We're using delta here as an arbitrarily change. So as we went from 0.99999 or -0.9999, right, And we got closer and closer to 1 to 0.99 and so on and so forth. That's our delta, how much we really just increment that value of x so we get arbitrarily closer to the point in question here. Okay, so we can conclude that it does not exist. Now, what you need to write down are, these are the cases when the limit does not exist. So there's 3 types of behavior that are associated with non-existent limits. Okay, the first one is an example of what we just did with absolute value. As f of x approaches a different number from the right-hand side or in the left-hand side as it approaches c. So the left-hand side and the right-hand side do not agree, like we just saw. One went to -1, one went to +1. The limit does not exist. Make sure that these are in your notes. You need to be able to look at this. Now the second one, f of x increases or decreases without bound as x approaches c. So this means what? When we're talking about increases without bound or decreases without bound, that means it's going to infinity. Say there was some sort of asymptote there and the graph just kept jumping all the way to positive infinity or going all the way to positive or negative infinity. So that's the other scenario. We're increasing or decreasing without bound. So there was an asymptote there, all right, and we get arbitrarily close to that value, but that value is infinity. We're going to deal with infinite limits later on in chapters, but not right now. So for right now, the limit does not exist because as x approaches that specific value, it increases to either negative infinity or positive infinity. And then the third rule here, f of x oscillates between 2 fixed values as x approaches c. Remember oscillating, so I want you to think of some sort of sinusoidal graph, which means what? It's bouncing up and down, so it cannot home in on a finite value. So as it oscillates between the 2 fixed values there. Okay, so those are the 3 behaviors where limits fail to exist. Okay, let's get into the formal definition of a limit. Okay, and you will have to apply what we just talked about on your homework assignment. Okay, so make sure that you read through the book and you take a look at a few of those other examples as well. So let's get through the formal definition of a limit. Okay, this is where it kind of becomes confusing, but once you understand this, I think you will have a really good concept of limits. And really this just comes down to change in y over change in x kind of scenarios here. Okay, but it gets a little messy because it's different nomenclature than you're used to of how things are written. Okay, so we are going to use the word arbitrarily quite a bit in here, which means we're going to get really, really close to a number, but we're not going to be that number. Okay, and we have to approach that limit from the left-hand side and from the right-hand side, and that has to be the same value. So remember, when we talk about this, we're going to say the limit of f of x as x approaches c has to equal L. Okay? And when we talk about this, we're going to say f of x is arbitrarily close to L. Okay? It can never be L in most of these scenarios, but it's going to get really, really close to L, so we say that that's the limit. Okay? It's very important. So remember, c is going to be the value in question, f of x is the function, and L is the limit that we're looking for. Okay? So, when we write this, okay, we use the Cauchy form. Okay? So, we use a delta and we use an epsilon. Epsilon's the amount of air in the y based on how much we move delta. Okay? What does that really mean? So, let's look at this graph here. Alright, c is our x value that we plug in, right? If I plug in c, my limit doesn't exist there, right? That means I get nothing, I get division by 0, or I get a hole in the graph. Okay? So when I plug in c, think back to the table approach that we did, right? We couldn't plug in our very first example, we couldn't plug in 1, right? We had x cubed minus 1 over x minus 1, and we couldn't plug in 1 because it gave us back, division by 0, so it gave us back a hole in the graph. So what did we do? We used a table, and we took that value, right? We did 1, and then we did a little bit bigger than 1, so we did like 1.0001, and then we did a little bit less than 1, so we did 0.999. Well, that's our Our delta is how much we did a little bit more than 1 and how much we did a little bit less than 1. So that's our delta, okay, as we changed a little bit around that value of C. All right, and what did we got? We got above 3 and we got a little bit below 3, right? When we plugged in, 1.0001, we got like 3.001 or something. We got a little bit above that value, and then when we plugged in 0.999, we got 2.99. Okay, that delta affects that epsilon. Okay, that epsilon is that change in y that's right. Our limit's 3, right? But epsilon is the value that we are above 3 on the right-hand side and below 3 on the left-hand side. So our delta affects our epsilon. And it's crucial that we want to make sure that when we do this limit in the formal definition of a limit, okay, that we stay within our amount of error, our epsilon. So we use our delta epsilon approach. Delta, just remember, is just a slight change in the x value around the point in question that gives us a slight error, epsilon, okay, above and below our limit based on our delta going above and below our C value. That's really what that means, okay? So we can use this and write this, and there's 2 ways that we're going to evaluate this, okay? We can say, and you're going to have to substitute this in when you do homework problems, so make sure that you write this down on our formal definition of a limit. So the first piece on our homework that you're going to need to use is the absolute value of f of x minus L is less than epsilon. So our homework problems are going to ask us about keeping a specific amount of error. What delta do we need? So this is the first part you're going to need to. And when you do your homework, you're going to substitute in f of x, the function. You're going to substitute in L, and you're going to substitute in the given epsilon that gives you. Okay? Usually it's going to be like 0.001 or 0.01, very small amount of error. Okay? And then we're going to talk about the phrase as x approaches C means there exists a positive number delta that lies on either side of the interval, right? C plus delta, C minus delta. So the other part that you need to focus on is the last thing on the bottom for your homework assignment, all right? 0 is less than the absolute value of x minus C minus delta, okay? Because we're going to solve for delta. We need to be able to find a way to relate the top and the bottom piece here, the 2 inequalities. We're going to be able to relate those. Okay, based on a specific epsilon, we can find a delta, or with a delta, we can find a specific epsilon. So we need to be able to go back and forth using the formal definition of a limit. Okay, so if we look at the first inequality, we're really talking about the distance between x and c, okay, is more than 0. And we want to talk about x minus c has to be within delta limits of that. Okay, so a distance of delta. Really, okay, so let's say delta is 0.01, all right, and we start at 1. Say C is 1. So we would have 1.01 on the right-hand side, and then we would have 1 minus 0.01 on the left-hand side. Does that really make sense? Kind of what we're going through? Okay, so you would have a number less than 1. All right, so let's write down the formal definition of a limit, okay? Now, it's important, we're defining it on an open interval containing C, and it may not exist at C, but C is on the interval, and it's an open interval. L, the limit L is going to be a real number. Okay, so we write this as, and we've already written this down a little bit, the limit as f of x approaches, or I'm sorry, the limit of f of x as x approaches C equals L. All right, meaning for that each epsilon greater than 0, and an error greater than 0, right, a little bit of change in y, there exists a delta greater than 0, such that, and these are the 2 important things that we wrote down on the previous slides, 0 is less than the absolute value of x minus c, which is less than delta, then f of x minus L, the absolute value of that minus epsilon, or is less than epsilon. Make sure you write all this down. It's these 3 factors that we're going to use the definition of a limit to do half of our homework assignment. So you're going to have to be able to apply these. Okay, we're going to be able to apply these. We're going to do an example here in a second. And all the examples should be relatively, similar to your homework assignment here. So let's take a look at this. So the example, we want to find a delta for a given epsilon. find a delta for a given epsilon. So we're going to start with the limit statement. So the limit as 2x minus 5 as x approaches, I'm sorry, let me rephrase that because I keep saying it kind of goofy and I don't want to get you confused. The limit of 2x minus 5 as x approaches 3 is equal to 1. Okay, so that's how we're going to say that. Well, we have to define everything. What's f of x? F of x is the 2x minus 5. L is equal to what? 1. And our c is equal to 3. We're going to plug in those three things into the two equations here, right? We're going to plug in c, and we're going to plug in epsilon, and we're going to plug in L, and we're going to plug in f of x. Okay, all of those are given to us in this problem. Okay, so the given epsilon for this problem is 0.01. So notice how we're substituting in f of x minus L. So that's where we get the 2x minus 5 minus 1 is less than epsilon. Epsilon is 0.01. Okay, it doesn't give it quite to you in the problem, but just know for this problem, epsilon is equal to 0.01. Your homework assignment, it will tell you what epsilon is. Okay, and then we have the other part of the equation. 0 is less than the absolute value of x minus c. What's c? C is 3, so its absolute value of x minus 3 is less than delta. We're going to solve for delta. Okay, so we want to make the equation piece, the inequality that's on the left, look very similar to the inequality on the right so that we can substitute in and use our epsilon piece to find our delta piece. Alright, so we're going to start by simplifying the left-hand side down. So we're not going to touch the delta piece. We're going to try to make the left-hand side look like absolute value of x minus 3 is less than delta, so that we can substitute in for the absolute value of x minus 3 to solve for delta. Okay, so when we do this, we're going to make the left-hand side there, and we're going to equate the two. Okay, so we're going to make the left-hand side, and we're going to start simplifying. So we have 2x minus 5 quantity minus 1. So we can rewrite that as the absolute value of 2x minus 6, right? Because negative 5 minus 1 is minus 6. Then we can factor a 2 out. So if we factor out a 2, we're left with 2 times the absolute value of x minus 3. Now we have something, right? That x minus 3 goes with our delta, right? Because our x minus 3 is less than delta. So now we can relate the two. Okay, so when we do that, we rewrite it. So we take our 2 times the absolute value of x minus 3 is less than 0.01, which is our epsilon, and we solve that for the absolute value of x minus 3. Okay, so you're going to take the absolute value of x minus 3 is less than 0.01 divided by 2. And then you're going to substitute that in for your delta. Right? Because it said the delta piece is absolute value of x minus 3 is less than delta. So we're going to replace that. So we end up getting delta is equal to 1/2 times 0.01. So that's our epsilon. We're really just solving that equation for epsilon, for the absolute value of x minus 3, and then we plug that in, and that's our delta. Okay? The 0.01 divided by 2 is 0.005. So we can say that the absolute value of x minus 3 is between 0 and 0.005. So our delta is 0.005. Hopefully that makes sense on how to relate the two, okay? And how we go through and how we go about using the formal approach. So now that we know delta based on our epsilon, okay, we can take a look at this on a graph and see how things look. So if we take a look at this, notice, all right, what's the value in question? Okay, our c isn't really going to change. Our c is still 3. All right, but we're zooming in, so you can see what the main graph looks like, right? So our f of x is 2x minus 5. Our value in question was as x approaches 3, right? What's the limit of, look like it's going to be? Well, we don't need to worry about it. The limit was given to us already, right? The limit was given as, what do we have there? I mean, if we just look at the graph, right, it's 1, right? There's a closed circle there. So the limit as x approaches 3 of 2x minus 5 is equal to 1. That was given to us, but that wasn't the point of the problem. The point of the problem was to find the delta given the epsilon. So remember, our epsilon was 0.01. Okay, so what did that really mean? Well, our y value was 1, right? Our limit was 1. So we wanted to evaluate, what happened when y was 1.01? Why 1.01? Because 1 plus epsilon is 1.01. Epsilon is 0.01. Okay, so 1 plus 0.01 is 1.01, and 1 minus 0.01 is 0.99. So that's our limit plus epsilon and our limit minus epsilon. We needed to find what the delta value is, right? Because our 3, when we had some sort of epsilon of 0.01, we had to find what that delta was. So our y value, or our x values associated with those y values, was 3.005 when we were at 1.01, and we had 2.995 when x was 0.99. Okay, so we had to find out what that delta was, and that's why that delta is 0.005. Okay, so hopefully taking a look at the graph really kind of helps explain this. You might have to listen to this part of the lecture a couple times, do a couple, the homework problems, or ask me questions, or rework this one on your own so that you can understand what delta and epsilon actually are. Okay, delta is the small change in x that we do to either side of our value c. That creates our value of epsilon on either value of either side of our y output. It really kind of breaks it down into basics on that. But anyhow, that's the end of this lecture. So that's the end of chapter 1, section 2. If you guys have any questions, please email me or ask me if you need me to zoom in and meet with you. So make sure you give yourself a lot of time to work on this homework. These problems, we're using the formal definition, are going to take you a little bit of time. Make sure that you truly understand how to get those epsilons and deltas and things like that. Alright guys, have a great day. I will see you in class.